everyone. Welcome to this new episode of the Swift Academy podcast. Today, I'm very happy to be with Dave Poirier from Canada, our iOS security expert. And today, we will try to. We are in the fourth episode of the iOS mobile security series. We have a lot of information to share today with you, especially about secure enclave, private key, public keys, and great practical session that Dave prepared to us today. Hello, Dave, and how are you?
Doing all right. Thanks for the presentation, the warm welcome.
Yes.
Happy to be here.
Okay. Last time we have spoken about a lot of things, especially about encrypting data, about how to use, how to try to use what we call the enclave secure. And today we try to have some explanation about how works secure enclave, and also distinction about private key, public keys, and all these things, all of these concepts about mobile security. I think that you have you shared in LinkedIn a great documentation from Apple about how secure enclave works. And before, in the preparation of this episode, you spoke to me about that as an introduction about secure enclave.
Sure. Let's share my screen here. That should be the one. All right. So it's true that when we gave all the demo before, we quickly went over like some example that we're using encryption. I didn't go into any depth at all about how each of these encryption actually worked or how to use them. So that's what we're gonna cover today. And because we're going to use the secure enclave for part of it, I just want to make sure that we fully understand how that works. So essentially, the secure enclave is on the chip directly that Apple provides, so directly in silicon. They have a part of the circuit that is designed completely separate from the system, so it's not reachable by the normal app. You have to make a specific memory access that you can do. So essentially via IO request, you can request from the security chip to do some encryption operation for you. Now that each chip, when they are first booted, they internally generate an AES encryption key that is unique for each chip. So
Okay.
Apple doesn't even have the ability to know what that encryption key is. It's directly in silicon. When first booted, it directly writes it to the NAND drive, and that's it. It's unique. So Apple doesn't have a way to stamp multiple chip with the same encryption key. We don't have a way to extract that encryption key from the silicon. The way the circuit is designed, the only way that we could potentially know, and I'm not even sure that's even possible, will be to have like probe directly on the silicon circuit at a nano level, like be able to see what goes on in the wires. But obviously, most people don't have that level of access, and I certainly don't have the equipment required for doing that. And I don't think many people do either. So as far as we're concerned, this chip that we receive is fully secure as its own encryption key. So directly on the silicon, there's that secure enclave AES engine, again with that key that is uniquely created at the first time the chip is booted up. And that key, that chip also has what we call a true random number generator. When we generate random number, we always use some kind of algorithm normally so you can use sequential random number generators where it will always give you the same sequence of random numbers, or you can use something that injects some more randomness. For example, you can use the system clock, you can use the temperature, you can use the microphone for injecting some randomness into your random number, the mouse movement, the keyboard, all of these elements. The more inputs you have, the more random the number will look to an outsider because they don't know what all these inputs are. So
Yes.
When you go with a true random number, Apple has created some kind of like circuit that has all the different types of input, like the temperature, the the exact positions of your iPhone for the gyroscope, and all kinds of different inputs, that makes it almost impossible for someone to replicate all the necessary inputs to be able to control what the next random number will be. This is what we call a true random number generators, is because there are so many different inputs to that number generators that it's impossible to predict what the next value will be. Because there's no way for us to predict what it will be, we can call it a true random number generator. If it's not true random, then it becomes a pseudo random number generator. And in most of the C library and system level access that we normally have inside of the iOS app, this is what we have, is a pseudo random number generators. But in this case of the security chip, it's a true random number. So when we're asking something from the secure enclave, we know that it's going to use its true random number generator and give us something that is really safe, really secure, fully random. It also has a public-private key architecture. So built inside of the security chip, it can hardware accelerate all the key derivation. So you can use public-private key, you can generate new public-private key, you can sign, you can derive symmetric keys from it. And all of this is fully protected with the memory channels. So when we are asking the secure enclave to create a private key, the way it works is that we're basically sending a message to that secure enclave chip or circuit on the chip, and the secure enclave will use true random number generator to generate a private key or the data for the private key. Then it will use the AES security engine inside of it to encrypt the key. Then it will give us a representation that it can understand, and send us the encrypted representation of the private key. So it doesn't give us the private key itself. It gives us a AES encrypted representation of the private key. Then when we want to encrypt, we then say, oh, I want, using that encrypted representation of my private key, I want to sign or want to derive a symmetric key from that private key. And you give that representation back to the secure enclave, it decrypts it, then it uses it. So what makes it secure is that since it's encrypted with that AES key that never leaves the security chip, only that security chip can decrypt the private key in order to be able to use it. Nothing else. If you give that same encrypted representation to another device, that other device will not be able to decrypt it because it does not have that AES key that is on the secure enclave, unique to your phone. Yes. So this is how your key are secure, because even if they are shared to another device or on the cloud, or your private key gets saved to disk or something like that, nothing can use it unless you have the secure enclave, that unique secure enclave of that phone. So this is why it's super safe, and it's safer than generating a normal private key that you have to then store in Keychain or store somewhere else, because these keys that are not created from the secure enclave are not AES encrypted uniquely for that device, and therefore they're usable, exportable, or hackable by third parties. But when you use the secure enclave, only that device can use it, so it's an extra level of security. But if, for example, you require a key that is usable by multiple devices, then you probably don't want to use a secure enclave, because then only things that are generated from the secure enclave are only uniquely usable by that device. So if you need something that is usable by multiple devices, you probably don't want to use a secure enclave. So that's it. Other than that, other than the fact that the keys are generated from the secure enclave, the APIs, the way we use the APIs are very, very similar. The only difference is that we put secure enclave dot in front of each of the P256 key types. Other than that, it's exactly the same API, the same functions, the same way the code works is compatible with or without the secure enclave. Apple made that very, very friendly for us. As long as we're using CryptoKit, it's super beautiful and works like a charm. So really, that's all it is. The secure enclave does not store your private keys. It does not store inside of its chip all the private keys that it generates, because again, it encrypts and gives them back to you. It's up to you to do whatever you want with it. Usually, you will store it into the keychain, which just gets stored into the normal system saving the keychain's storage space, which is on the NAND drive, on the flash drive of the device, accessible by your app, and with the same security. Like you can say, I want my key protected by biometric, two-factor, whatever you want. So you can use the same keychain storage mechanism as usual, but again, it's not the secure enclave that stores the keys. A lot of people think, oh, my key is actually stored in the secure enclave. It's not.
Secure enclave.
The secure enclave generates the key, encrypts it, and gives you the encrypted version of the key, and you do whatever the hell you want with it. And then you give the encrypted key back to the secure enclave, it decrypts it, uses it, and destroys it. Well, it doesn't destroy it, but it removes it from its own internal memory once it's done with it. So you are responsible for storing that secure enclave encrypted private key.
And this is the same mechanism also for iOS, and if you are in the iPhone and also in the MacBook, the same mechanism for securing enclave in the MacBook, the same like in the iPhone.
My Apple, once they moved to their own chip, they made sure that their own chip was used on the iPad, the iPhone, the Apple TV, on the Mac OS, everywhere where there's a security chip is the same mechanism.
And what kind of relationship between the keychain and the secure enclave? When we speak about that, we cannot record the private key in the secure enclave.
Yeah, you can you can basically CryptoKit has been modified to be able to request from Keychain to create a new private key that will be stored in secure, like managed by secure enclave. So you can request a key and Keychain will then communicate to the secure enclave and say, "Hey, give me a private key." Keychain will generate the private key, encrypts it, give it back to Keychain, and Keychain will store it. And then when you request the key, it just gets retrieved from Keychain, and then you can use it to make to encrypt and whatnot. But it's still just the same. You could, if you wanted, speak directly to the secure enclave, get a key, and then store it yourself. And
no need to pass by the Keychain. Yes.
So the relationship with Keychain is just happens to be a store. Is it needed to store the secure enclave private key inside the Keychain? Absolutely not. You could store it into your own files because it's already AES encrypted by a key that is only uniquely stored on the secure enclave. So it's already encrypted. So you could store it into user defaults if you wanted to, or a file. It doesn't matter. It's already encrypted.
That's great. Maybe we can, we can pass to the how we can a practical example of how to store and retrieving a private key using the example that you have prepared for us.
So we're gonna run a little app later on, but for now, let's go over the code. So this is a view here that is called P256 encryption view. We're using CryptoKit, and this is how you generate a secure enclave key. You simply say request from secure enclave to give you a private key. Now I have two examples here, a server and a local. It's just in my example, I have two different keys, and I want to derive a symmetric key from that. But for now, let's focus just on one of them, the local side. But essentially, it's just how it works. You just create a secure enclave key. You say secure enclave.p256, and you get a private key. From there, if you want, you can get the public key. So all you have to do is say, from the private key, give me my public key, and it will just give you your public key out. And then if you want to encrypt or derive a key, so this is how we derive a key. So we have our own local encryption key. So it's the local private key, and we can derive a secret using a public key. So anyone wants to, let's say a server or wallet, you have your own private key. I have my own private key. You give me your public key. I give you my public key. So we exchange public keys because they're public. It's fine for us to share them. We each keep our own local private key in our apps. So I keep it in my app. You keep it in your app. And so that in order for us to be able to encrypt, we're going to derive a symmetric key that can then be used to do AES encryption or another type of encryption. So you first derive what we call a shared agreement or shared secret from a key agreement. So I have my private key, you give me your public key, and from that I obtain my shared secret. Using a shared secret, I can then use a key derivation algorithm. So this is using HKDF is a Hellman key derivation algorithm.
Okay.
And then you specify which salt you want to use, or which hashing algorithm you want to use. Shared info is some kind of things that we previously agreed that we're going to use as a basis. So you can say, for example, it can be just a normal string or any kind of data packet that we have previously agreed upon. So
Okay.
we agreed that, say, the password is Alibaba,
Okay.
or Open Sesame or something like that. So we have a shared agreement, a shared sentence that we previously agreed upon, that all the members of the community that are allowed to exchange messages, let's say WhatsApp. So this is a WhatsApp shared info agreement. We everybody that use WhatsApp have that same shared info that we were able to derive. And then we have a salt that is normally unique for each communication or each message or each packet. Each file that you encrypt normally will have its own salt. And then you also specify the size, the number of bytes that you want. Because we're using AES 256, we want 32 bytes of data in order to be able to recreate the 256 bytes key. So this is what this output byte count is. It's simply the size of the symmetric key that we want. And
Okay.
the shared secret that we have received will be able to derive that key using that hashing algorithm, the salt, the shared info, and the number of bytes that we requested to be able to generate that symmetric key that is exactly 256 bits long or 32 bytes. And then we convert that key into a data object so that we can then use it later on. But in theory, if I was chaining the encryption directly, I will not need to convert that symmetric key into a data object. It's just that I want to be able to represent it on the screen and makes it easier for us to represent if it is as a data object than an actual symmetric key that is then usable for doing the symmetric AES encryption. Short things is just we're using the local private key with a public key to derive a shared secret. We use a shared secret to be able to derive a symmetric key, and then we use a symmetric key to do the symmetric encryption using AES 256.
Okay. Great.
So let's go into maybe the runtime example. See
Okay.
if that works in practice. So we go into the 56 encryption. So we have the local key, the server key that I mentioned before. So I don't display the private key because they're private, right? I should not spoil the beans. Their private keys are not supposed to be public. So I can generate private keys. Each time I generate a private key, I have a different matching public key. And this is the public key here that are being displayed on screen. I can do the same thing on the server side because I want to be able, in this example, to control both sides. Makes it easier for me. So this is like I communicate to a different third party. So this could be Walid, then this could be Dave, could be someone else. It doesn't matter, or a different server. But I can generate multiple different remote side public key right now. Same thing for my local keys. I can generate multiple instances just because I want to quickly create it. And as you can see, Secure Enclave is really, really fast. It's as fast as I can click it. There's almost no delay. It's hardware accelerated key generation, so it's blazing fast.
Compared to other kinds of private keys.
Well, if I want to generate something, first all the encryption, not all encryption, but most of the CryptoKit supported encryption algorithm are hardware accelerated on as long as you use the Apple hardware. So if you're using CryptoKit, most of the time it's hardware accelerated. There are some algorithms that are not. And if you were to use Common Crypto, for example, or if you were to use another third-party library that doesn't use CryptoKit or Common Crypto but implements their own, let's say you have a C library that is able to do P56 encryption. Usually that C library will not use hardware accelerated functions to be able to do it. It will just do it in code. And it's about 100 times slower. So the fact that we're running on the hardware means that we're going to be able to do hardware acceleration, which runs about 100 times faster than the normal C functions. So there's always benefits of verifying whether or not the algorithms that you pick are hardware accelerated. As long as you use CryptoKit, most of everything is hardware accelerated, so you don't have to worry about it. For sure, if you use elliptic curve cryptography, P256 curve, so the P256 is hardware accelerated, guaranteed. And if you use AES GCM, that's also hardware accelerated. If you use a different AES mode, it will not be.
Okay.
Apple really recommends using the AES GCM, which is I don't remember. It's Galois counter mode.
Okay.
So as long as you use AES GCM mode, it's fine. You will be hardware accelerated. So I always recommend using AES GCM and using P256 just for having that hardware acceleration, regardless of which of the Apple devices that you use. And as I explained, so we have a public key, we have a private key. This happened to be the salt that I use, but I can generate new salts as desired. And the shared info, in this case, I kept it the same. Again, it's uniquely generated every time we launch the app. We get a different shared info. But in this case, in this runtime, this is the shared info that we have. And we can derive the AES encryption key or the symmetric key using this information. And we see here the locally derived AES key is this one. And if we do the same derivation with the same keys without changing them, so when we do it on this way, it's going to use the server private key with the local public key, but with the same two information, and we're going to get the same AES encryption key. So this is how we are able, from the server side or from the client side or from your side and my side, we are able to derive the same symmetric key, even though we don't have the same information, because I have your public key and my private key, and you have the reverse. You have your private key and my public key. So using those two different bits of information, we're still able to come up with the same symmetric key to decrypt because of that shared secret that we were able to create, and because we have the same key derivation algorithm that we both agreed to use. Now, obviously, if I use a different key derivation algorithm, so let's say I use a different shared info than you, or a different salt. So if I use a different salt, look, my keys are not the same anymore. So we won't be able to do encryption between the two of us because I use a different salt. But if you use the same salt as me, it's fine. We're able to get the same keys. So it's why. So when we're developing those encryption system between multiple people, we have to get some of the basis and agree between each other that we're going to use the same stuff. So when you speak to your server team, it's very important that you agree how we're going to derive this, which hashing algorithm we're going to use, what's the shared info, how are we going to come up with the salt? How are we going to, am I going to give you the salt all the time? Is it a salt that you derive from something else? Is it a random salt? Is it attached to the encryption packet? Like, do I create a packet that has a salt included into it and encrypted bytes after it? You have to agree how we're going to transfer or come up with that information. And then after that, I just give you my public key. I keep the private key secret to my side, and we're able to exchange data and derive those AES keys that we can then use for encryption.
Great.
Blurry enough?
I think. Yes. And yes.
So maybe before we go into all of this, I can go back to the basic of encryption, if you don't mind.
Okay. Yes. I think it's very important. Yeah.
So the very basic, the very first thing that we have to understand, I mentioned a SHA 256 when we were deriving the keys. SHA 256 is what we call a hashing algorithm. The way it works is that you give it some piece of data, like this, like hello world, which when we encode it into UTF-8, it becomes that hexadecimal string right now. But if I shorten it, obviously, so A has its own code, B has its own code, and C has its own code, right? This is just ASCII. We know that stuff. So working with Walid at the moment. So as you add more stuff into it, your UTF representation will grow because we are adding more digits into it, right? But the hashing algorithm, because it's SHA 256, it will always generate the same 256-bit value as an output. and it has a very complex mechanism inside of it. And the good thing about this is that the hash doesn't tell you how long the string is. So there's no way for you first to know how long whatever the original source of data
Yes.
was. It can be
Yes.
empty, it can be 1 byte, it can be 2 byte. It doesn't matter. The output is always the same length. So
This
right
is a
away,
power.
just from the output, you cannot tell what is the same length. Versus when you're looking at UTF-8 data, obviously it grows and shrinks as I input stuff into it, but the hash is always the same size. So already there's some type of information that we lose by going into an SHA-256, and we want to lose that. We don't, for example, when I have a password as an input, I don't want to be able to tell how many characters are in my password. I just want to know, is it the same password or not? So hashing algorithms are very, very good for this. Is when we want to compare password, we went into this in previous episodes where we were storing the hash inside of a database. And this is exactly why we want to use that, is because we don't know how long the password is. We just know what the output hash is supposed to be. So if I have a password hash here, say my password, this is the hash that I get as an output. And I can delete this. So it starts with DC, ends with 2A. If I delete this, I have a different hash output. But if I retype the same password, it starts with DC, ends with 2A. It's the exact same sequence that we get as an output hash. So we're able, just by comparing the hashes, to know if the input password is the same or not, because we get the same hash, and we still never had to store the password inside of our database. So it's safer. The problem now is if we don't use what we call a salt,
Yes.
we can tell if two users have the same password because they both have the same hash. So if I store my password, you store your password, we both store it into the same database, we can say user A and user B have the same passwords. Why? Because they have the same hash into the database.
Yes.
We don't want that.
Yes.
We don't want to be able to tell if two users have the same password. So one of the concepts that we have to do when we're developing those databases that stores password is the concept of a salt. A salt is something that you inject into the algorithm that's gonna throw some weird, like different values into the mix. So when we generate a salt, we combine the data that we want with the salt, and then we give the two pieces together to the hashing algorithm. Literally, we just have we generate 256 bits of random data, and we combine that with the encoded string, and then we pass both of these things because we already saw that regardless of the length that we pass in, the output is always the same length. So we use that property of the hashing algorithm to also inject our own random bits in front of it. And every time we generate a different salt, the output will be different. So that means that when I store my password, at the moment, just before I store the password into the database as a hash, or the hash of the password into my database, I generate a brand new salt. I compute the hash based on that salt, and I store both the salt and the hash into my database. Next time I want to verify my password, I take my password with my salt, I give that to the hashing algorithm, and I can then compare whether or not the values are the same. But because your salt, every time you store a value into the database, you generate a brand new salt. It means that my password and your password can be the same, but because they have different salt, they will be stored as different values into the database. So I can no longer tell if two users have the same password. I can still verify each of the passwords because I have the salt and the hashes into the database, but at least I can no longer tell if two users have the same password. Brings the security level layer up.
Yes, very important. The set. I didn't know about it before because I know that the possibility to have two password, the same two password for two users, very. It's not very high for me, but we can have this, and it can help the system to be more secure if we have this kind of salt. And the salt is generated by this. It's like a consensus when
Well,
we try to
in
have
my
the salt.
case, yeah, in my
Okay.
case, I generated the salt using a small function that I created.
Okay.
So, where is my salt function? This is signing hashing. There we go. So when you use CryptoKit, there's something called the symmetric key that you can create, and the symmetric key you has some kind of random algorithm built in. So when you say give me a new symmetric key, it gives you not random bytes that are of the size that you specify. So here I simply say give me a new symmetric key that is 256 bits, and then I convert that into a data object, and that becomes my salt. This is probably the safest way that you have of generating random number. Of course, you could use a loop instead. So if I wanted to, I could, for example, var my random data equal data, and then I can use a for loop for I in 0 to 32, and then I say let byte equal you int 8 dot random in 0 to 256, and then I can say my random data plus equal my data of my byte, and then I can return my random data. That will work. It's just that the uint8 random function is a pseudo random number generator. We
Yes.
don't want pseudo random. We want as much randomness as possible. So when we use the symmetric key, it uses a better
Kind of strange.
randomizer.
Yes.
It used the best randomizer available for the system to be able to generate that symmetric key versus just uint8, which will use the fastest. So instead of using the best randomizer, it will use the fastest randomizer because it doesn't
Okay.
require security. So you want to use the best randomizer possible, and that's available directly using symmetric key. Obviously, there are some lower level functions that you can use to do this that will still give you those same safe random, like the best randomizer possible. But it's just easier to simply say, I want 256 bit, give me the data. And then if you want something smaller, you can always say, I want 128 bits, 198 bits, or you can simply generate 256 and then just return part of your key. So you can say, let my data, and then you can say my data, I want the first, I don't know, 16 bytes only, or the first 3 bytes. And that will give you your like only that small subset of data, and that's fine.
That's fine.
You want to. That will still give you true random or close to true random as possible, random data bytes of the size that you desire. In our case, it's just again easier to use something that is natively supported. So 256 bits, best randomizer possible, symmetric key. We convert that into a data object. Boom, we got our random key. So this is why I use that, but you can create your own function.
Yes. Great. We have some, I think, basics about hashing. Now we know the role of salt, how
Correct.
to distinguish between kinds of algorithms like UTF-8 and the SH3
Correct.
256.
There are a lot of different hashing algorithms that exist.
Yes.
Blade 3, MD6, SH256, RipMD, Whirlpool are all pretty much current safe hashing algorithms that are ready for us to use. There are older ones like MD5, MD4 that were
Yes.
versions that have now been proven to be insecure. And the reason why they are insecure is just simply because of the amount of the cheap available storage that we are now able to buy. Back in the day, the biggest hard drive that you could buy was a 40 megabyte hard drive. So it was inconceivable for someone to use 16 gigabyte of data to create a lookup table for MD5. So people were like, dude, I can create an MD5 algorithm. Nobody has enough storage to quickly be able to create a lookup table. So I'm just going to, it's safe for us to use because we have 40 megabyte hard drive. But now that we have gigabyte hard drive, MD5 is no longer secure. So we need MD6 or SHA-256 because storing all 256 bits possible outcome with what was the input data that generated those outcomes is inconceivable. It will require like 256 bytes of data just for the output value, and then storing also the possible input values for each one of those outputs. It completely makes no sense for 256 bits in this day and age. Now, some day in the future, it might be possible to have a laptop with 6 petabytes of storage. If that day comes, then SHA-256 and MD6 will no longer be valid, and these algorithms will be trashed and will be replaced with MD7 or MD8 or SHA-512, SHA-1024. These already exist, but there's no reason for us to use them. They're just overly complex, and they're not hardware accelerated at this day and age, at least not on Apple. So again, stick to what is hardware accelerated. Stick to SHA-256 on Apple, and you'll be good to go.
I have a basic question about these algorithms. How they can be validated? There is an organization that try to validate this kind of algorithm, or this is only work at the university, like MIT, something like that, Stanford.
It's a valid question. It's a valid question. Essentially, anybody can come up with an algorithm. It's an open. Yes. Anybody, I can decide to scratch on paper an algorithm and say, "Hey, I created my own hashing algorithm. Please use this." And then first, you're gonna have to have some third-party review. So you maybe submit it to your friend and say, "Hey, does it make sense? Is it safe?" And then your friend may think that it's safe. And then eventually you may work to send it to a cryptographer, a guy that works in cryptography or study cryptography. And then he will look at it and say, "Yeah, that looks kind of weird. I think if I do this and this, I can figure out what the output value will be." And they're like, "Oh, okay, it's not safe." So this is pretty much how it works. You just submit it to people that are going to review it. Some people will try to break it. And then after a while, if you submitted it to hundreds, thousands of people, you submitted to different cryptographers around the world, and all those cryptographers said, "You know what? It looks safe. I'm not able to find any fault with it. I tried to break it for weeks. Nothing is there." Then what you can do is you can open a contest. You can put it publicly on the internet. You can say, "Here's my hashing algorithm. If someone can break it, I offer $1,000 reward." If nobody comes up after a month for $1,000 reward, say, "I broke it," then you're like, "You know what? I have an open contest, $1,000, nobody broke it. I'm gonna up the antes. I'm gonna say for $100,000 if somebody can break it." So you up the antes a little bit, and you offer someone a bigger amount of money if they can break it. So hackers start to be interested into that contest, and you have more hackers participating into that contest because some people are willing to spend a little considerable effort to try to get that $100,000. So as you up the antes, more and more people will look at it for a longer and longer period of time. So if your algorithm has been publicly advertised for 3, 4, 5, 6 years for a considerable amount of money, you know that there's been a lot of people that has looked at your algorithm, and there's discussion. You can have a discussion forum. You can have a place where, like a GitHub page, for example, where people can discuss. And you can see these discussions. Nobody has any issue with your algorithm. There's millions of people that have reviewed your algorithm, millions of people that has talked about it. You have confirmation that some cryptographer has spent a considerable amount of time on it, and nobody broke it. Well, after X number of years, your algorithm become certified. Or it's not certified, it is considered safe. Because the hacking algorithm, the cryptography the community has not found any fault with it.
Okay.
So it is considered safe until proven otherwise. At some point in the day, some security researcher may say, "You know what? I broke it." That security researcher will have a stamp, say, "I broke SHA-256. I found the fault with it. I know how to break it. You just give me a hash. I can give you a possible input that will generate, like, very quickly. I can give you a possible input that's going to give you that specific hash." If someone is able to do that, they will have broken the SHA-256. And we will now have to move to something else. That's just how it works. It's the community. The algorithms are open. You publicize them. You make the algorithm public, open source. It's the only way people will trust it is if they can look at the algorithm. If you give them a black box, you say, "Trust me, it's safe," nobody will trust you.
Yes, it's normal because what I thought before that you can pass it by kind of university, some security researcher to validate this, and kind of
it's a first step. Giving it to a single university, to a research, to a cryptography, to a couple cryptographers in the university, and say, "Can you look at it?" is the first step. But you will definitely not have wide industry adoption,
Yes.
or I will not even personally consider an algorithm safe if it's just validated by two guys in a university.
Yes. Yes.
Maybe they just didn't attack it by the right angle. Many of those algorithms were broken over years. Sometimes it took
Mm.
years, sometimes it took like hundreds, thousands of hours, 10,000 hours before they were able to break it and prove that there's a way to get the information out. Um, Algorithms are sometimes safe for 15, 20 years. And then after 15 or 20 years, we're like, oh my God, yeah, it's not safe. There's this angle attack that we never thought about that we can actually do. So considering something safe after a couple months, sending it just for one university, absolutely not. In order for algorithms to be safe, they have to be evaluated for over a longer period of time, with normally some monetary reward open to the public, and over a given amount of time, like say a year, 2 years, 3 years, 4 years, 5 years. You don't trust an algorithm just because someone hasn't cracked it in the weekend.
Great. Now I think that we can pass to the AES encryption because
Yeah, sure.
we did. Yes.
So AES encryption itself, that algorithm will work with different key length. And the way it works is that the algorithm inside has different algorithms. So there's 128, 192, 256, 512, but they all kind of works the same way. We won't go into all of the details. If you want to see how that
Yes.
the actual algorithm works, go and find those research papers that talk about how that works. We don't have enough time to be able to go into depth into it. But the way we use it as an iOS developer is that we generate an AES key, or we derive an AES key, because we saw how we can derive a key in here. Once you have your encryption key, you can have your piece of data. Now, for sake of simplicity, I have a string that I encode to UTF-8. Then using my key, I can encrypt that data, and then I can decrypt it back. As long as I have the same encryption key, I can decrypt the data back and get the original out. Now, when I encrypt using CryptoKit, what I get is a sealed box. So I create a symmetric key using that data. I have my data. Using the symmetric key and my data, I get something called a sealed box. And the sealed box has a property called combined. And that's what you normally will save, is the combined data of that sealed box. And what it contains is a nonce, or what we call a salt. You remember when we said we should have a salt every time? That's exactly what this does, is that when we encrypt it, it generates a salt for us. So CryptoKit will generate a salt for us every time we generate using CryptoKit. If you were using Common Crypto, you had to come up with your own salt. And people misuse that or incorrectly use that, because very often people would have a salt baked into the code. It will be the same salt all the time, or they would encrypt like they would create multiple files that will be encrypted with the same salt. And you absolutely should not do that. Every single time you encrypt a piece of information, you shove its own salt. It generated every single time you encrypt. Again, because of the same reason for hashing, if you store the same value twice, and it has the same salt, it will have the same output.
Yes.
You don't want two files that have the same content to be encrypted and to be able to say those two files are the same. Because you don't want that, you need different salt every time. Then if the file contents are the same, they will be encrypted with different salt. So you will not be able to tell that the two original files are the same. But if you use the same salt, you will be able to tell. You don't want to be able to tell, therefore you use different salt every time. In Common Crypto, again, you had to generate your salt yourself and give it to the Common Crypto algorithm. In CryptoKit, it's done for you so that you don't screw up. So every time you ask for an encryption, it automatically encrypts with a different salt every single time. You can see that nonce there. They called it a nonce because it's a salt that is used only once. So they called it a nonce. But it's still just a salt. It's a random value that they inject every single time that you encrypt. And that value varies every single time. Because that salt varies, the output here for the remainder of after 183 in this case, so the 934 blah 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 blah, this happens to be the well, I don't have any data here. So let's create some data and encrypt. Here we go. So after the 36C, so 36C is right here. So it starts with 92946 all the way till I reach the AEAD, which is right here. So CCF. So from here to here, this is the encrypted value that I had. If I decrypt it, I get hello data. So this is the length of data that gets encrypted using AES 256. And it's somewhere in here. So I have first my nonce, then I have my encrypted data, and then I have what we call an authentication digest. As part of CryptoKit at the end of the encryption, it generates an authentication digest that confirms that the salt and the encrypted data have not been modified. So there's some kind of algorithm like this. You can see there. We can go into more detail into another episode in the future. But that authentication digest get created. If you modify any of the digest, like I'm modifying here, you can see some bytes changing every time I click. If you modify any of the data and then you try to decrypt, the CryptoKit will first use that authentication digest to confirm if the nonce and the data are valid. And there it will not be a match. The authentication digest will no longer be a match for the data that is before it, and AES will not even try to decrypt the data. It will say, you know what? The authentication digest is invalid for what you gave me as a sequence, so I'm not going to be able to use it for decryption. So CryptoKit has that authentication digest that is built into it. It's called AEAD, and it's automatically generated for you for CryptoKit. So safety, yay, extra safety for us. So it's one of the beautiful thing about this. So again, working with Wallet, we're using this and this. We can encrypt it. It gives me that sequence, and then I can decrypt it. I get my data back. So as long as the sequence is not modified, the AEAD will be valid for the nonce and the encrypted bytes that I have. And then obviously, if I don't have any data, let's say I don't have any data here, it's the simple, like no data. I just have a salt with no data. My authentication digest, you can see it. I have 922 D98. It ends right here. That's my nonce. And then you can see that right after my nonce, I have the authentication digest that starts immediately there.
Oh, okay.
So one of the property of AES encryption is that we can kinda, and I say kinda here, we can kinda
detect
how long inside is. Because if I have my nonce and I immediately have the bytes of the AEAD, I know that I basically my encryption is encrypting nothing. I have no input data. So even though I have a sequence as an output that is looks random, I cannot really tell that you're encrypting nothing.
Yes.
Just because I know. But as soon as I had one byte inside of it, the digest is going to skip not just by one byte, but by a certain length. Actually, is going to increase by one AES block. So, boom, you can see right away it encrypted. So I have 60 here. That ends right there. And then I have 16. It starts right there. Actually, my authentication digest is what controlled the output. So the output is actually right here by 1. So you can see it increased by a step. It jumped by a block. It's not just by 1 byte or 2 byte. It jumped by a sequence. So working with, again, boom. Every single time I have more input data, the sequence increases in length. So you can kind of tell the input size of the data when you're using asymmetric encryption. And you could not tell when we're hashing, but you can tell when you're encrypting approximately how many bytes of input you have. You can still not tell what the data is because it's encrypted. And unless you have the encryption key, you will not be able to decrypt it. But you can you can at least tell how big the input data is approximately.
Okay. And this is the same mechanism also for plain text or for another kinds of data like image, video, etc.
Essentially, it works with bytes, right? The AES
With
encryption
bytes, yes.
algorithm works with a sequence of bytes. This is why I'm doing the UTF-8 representation here to show you the bytes.
Mm,
So I
okay.
have a string. I happen to be encoding it in UTF-8. It could be encoded with anything else. It could be an image, like you said. It could be a text file, an image
Image.
file, a video file. It doesn't matter as long as
Mm,
it's data. Once you have the data,
okay.
you can encrypt it with AES and you decrypt it back. And I just happen to know that because of my app, I can trust that what I have here is a string because I know I created a string initially. So I try to do
Yes.
UTF-8 decode the data back into a string. But
Yes.
the AES encryption works with data only. So let's go into the code and look at it.
Okay.
So we have the AES encryption view here. First, we have a symmetric key, exactly like we had in the other examples. We have a symmetric key that is of 256 byte, and every time I want to generate a new key, where I simply create a new symmetric key. So when we go into the app and we say generate a new key, this is all it does. It just asks for 256 bits of random data as a symmetric key. So I store the symmetric key here. And so every time I encrypt, if I have the same key, it encrypts the same sequence, so or a different sequence because I have different nonce. But if I have a different key and I try to decrypt, let's say I encrypt here and then I generate a new key, I will no longer be able to decrypt because I don't have the right encryption key. So the way encryption and decryption works, so when I want to decrypt, I call my decrypt function. When I want to encrypt, I call my encrypt function. So let's go and take a look at how those works. So my encrypt function takes my raw text, my hello wallet that I was entering. Then I take the data of that object. So that's my input data because I encoded it with UTF-8. My input data is now my UTF-8 encoded string. And then I create my, again, this is where you were saying, like, can this be an image or video or recording or anything else? Yes, your input data can be anything. And then I use the AES GCM, the Galois counter mode version of the AES algorithm. And using my symmetric key that is 256 bit in length, I can encrypt or create a sealed box, which is the encrypted version of my data. So my input data, I give that to the seal and I get a sealed box out of that. So that's the AES GCM sealed box. It's specific implementation of the sealed box for the AES algorithm. And then I grab the combined data. The combined data is the one that has the nonce, the encrypted, the ciphertext or the encrypted data, and the authentication digest at the end. And once I have all of that information, that's what I will return. I set my value here to ciphertext of my Swift UI view, which is here, and that's all it does. So it just basically says, and it resets a few value in my Swift UI view, but that's all. Once you have the combined data of your sealed box, your data is encrypted. That's the ciphertext output that you would send to your remote party user, or that you would store in the keychain, or that you could store as an encrypted file on disk. So once you grab the combined data, you have everything. Well, as long as you have the encryption key, if you have the encryption key and the combined data, you have everything needed to be able to decrypt and re-encrypt the data as much as desired. And when we take the same ciphertext that we saved from the combined data, so we take the ciphertext and we create a sealed box from it. We basically say AES GCM sealed box from that ciphertext. It was a combined data object, so we grab the combined data here, which has the nonce, and the ciphertext. We could create it a different way. So if we go here, my other sealed box, we can try to do AES GCM sealed box, and you can see it can allow you to specify the different components of your combined object. You can say, this is my nonce, this is my ciphertext, and this is my tag or my authentication data. So you can manually specify them if you want. But if you use the combined object, you already have all three. So, but you could send them separately if you wanted to, like for whatever reason you want to send the nonce via an email. Then you send the ciphertext via a file transfer, and you send the tag via an envelope that you mail to the person. You could do that, but So you could send data whichever way you want, but in this case, it's just simpler sometimes to just have all the combined data.
Combine it.
By the way, as long as they don't have the encryption key, it's safe for us to send all of that data in one shot. The authentication doesn't contain anything that will prevent someone from decoding. It's just the EAD at the end. You could actually skip it, but CryptoKit needs it because CryptoKit has the authentication digest built in because it's the best practice to do. But you could use Common Crypto to just use the nonce and the ciphertext to be able to decrypt your data, even without the AEAD authentication digest. But CryptoKit requires it because it's built in. It wants to validate that you have the right data. So anyway, you create a sealed box using your combined data, which is the nonce, the ciphertext, and the tag. And once you have the the sealed box, you decrypt it, or you open the sealed box using the symmetric key and the sealed box, and you get the decrypted data out. And once you have the decrypted data, you can do like I'm doing, and you can try to decode it because we expect it to be a UTF-8 encoded string, so we decode the string back as from UTF-8 data. So that's all the encryption and the decryption does is simply the encryption takes your input data, creates a sealed box from it, then you grab the combined data output of your sealed box that has the nonce, the ciphertext, and the tag, and then you recreate the sealed box using the nonce, the ciphertext, and the tag into a sealed box, and then you open the sealed box using your symmetric key. So simple like that. You just use AES encryption, which will be hardware accelerated on your iPad, on your Apple devices.
Great. And now we have some understanding about
correct
AES encryption, the basic of hatching.
Correct. So we can bring us to the P56 encryption. And really, when people say it's P56 encrypted, they're kind of lying. You don't encrypt with 2P56. You derive encryption key with P56, and then you use an AES symmetric encryption for your P256 by itself does not encrypt. P56 is just a curve. It's an elliptic curve cryptography. It's used for deriving encryption keys, unique keys. You can use that for signing. You can use that for key derivations. But P56 by itself does not encrypt, and that's a bit of a misnomer. We say, I'm going to P56 encrypt my data. No, you're going to use P56 to derive your encryption key, and then you're going to use a different algorithm for encrypting. So I use the term P56 encryption to mean key derivation. And in this case, I want to, like in the code that we went before, we derive my 256-bit encryption key so that I can do my AES encryption. So I derive my encryption key using my P256 public and private keys. No need to go more into details. We already covered that,
because we covered that, And
now,
the difference...
We also have signing. The difference between encryption and signing. Encryption takes your raw data and change the form so that it's no longer representable. Like we saw here, like we have this bad sequence of data, and it looks like this, which is not the same sequence of data at all. And then when we decrypt it, we can get the data back. So that's encryption. It converts from what we call plain text into what we call ciphertext, or just what looks like random data to somebody coming in. So that's encryption. Now, when we go into signing, we no longer modify the input data. We are just trying to confirm that the input data is exactly the same. It comes from the person that sent it to us. It's basically validation. It's my stamp of approval. It's Dave. I put my thumbprint on it. So when I'm sending a piece of data that is signed with my P56 signing key, I essentially put my thumbprint on it, saying it really comes from me. Nobody else has my thumbprint. It's me. And only me. So when I give you the data, you can confirm that it does come from me. It doesn't come from a third party, or it doesn't come from a hacker. So it allows you to confirm that the data or the request that you have received is indeed coming from the person that is, or the computer that it is supposed to be coming from.
Yes.
So
to
this
be more confident.
you can be more confident that you can then decrypt and use the data without it being some kind of malicious payload that's going to hijack
Yes.
your system. But that's what signing is for. Normally, you would do encryption and signing in the proper system. So if you have a proper security mechanism, when you are sending an encrypted file over to a server, you would not only send the encrypted file, you would send the encrypted file with a cryptographic signature, and then the remote party will verify the signature to verify that the data comes from you, and then after that it will try to decrypt it using, again, your public keys. You can see that when you're going on for watching some Linux distribution on the internet. So you go and you can go on the internet, for example, and you can say Debian distribution
Yes.
signature. And when they're disputing, you can see here they're giving you the public keys and they're giving you the fingerprints of each of the distributions. So you can import the public keys for the identities of each signing key. When they're creating a distribution of Debian Linux, they are signing the distribution with their public keys. So they have an RSA public key here. They're not using P56. They're using RSA for public-private keys. But whether you're using P56 elliptic curve signing or RSA public-private keys, the logic is all the same. You have a private and a public key that allows you to generate a signature. And so they give you all the details in here. And whenever you go and look at one of the distribution, it will have a signature built in. So if we go Debian, we should be able to find a distribution somewhere. Debian, if I click download, will it bring me to a download page? It wants me to download. Cancel that. Other downloads. There should be a way for us to see. There we go. So we have the 180 for ARM64. I want the ISO CD. And you can see here each of the files. So it has the file here. Well, let's see, make sure that my browser is fully visible. So this is the file here that you would download, the ISO that you would burn on a CD and be able to use. And it has the different signature that is unique to each one. So this is a PGP signature of to validate that this build really does come from Debian, the Debian team, and not a hacker that was able to put their image onto an FTP server so people download an image that is already corrupted. So a lot of people would just download the image straight as and burn it, but the proper way of downloading a distribution would be to download the ISO, then compute the signature and validate that the signature matches one signed by one of the public key from Debian, the Debian team, which was available right here.
Okay, great.
So the people that do care about security will definitely be doing a lot of that. They will use the signature using public-private key signing to validate that the stuff does come from them. So it allows you to put it on public website and still have some kind of trust that the website has not been hacked because you can validate the data. This is also how you can validate that the data has been hacked, is because you're able to compare the signature and they no longer match. And you're like, hey, the data on that server is no longer coming from the Debian team. It's from some third party that we don't know about.
Yes.
And so the signing, the way it works is it's a little bit like an encryption. You generate a key, a private key, and you keep the private key private, and you put the public key available to the third party, like the Debian team put they directly on their public website. The Debian team have their public key on their website. So you could do the same. You could send the public key to anyone. You could put it on your front door. It doesn't matter. And in this case, my public key is right here. And then you have some kind of data. So again, I'm just going to use a string that I'm going to UTF-8 encode to be able to generate, but it can be any kind of data, like the ISO image that we saw from the Debian team. And then once you sign it, you get a unique signature here. And again, because you're using CryptoKit, Apple was bright and intelligent. They're using a salt that is included inside of your signature. So every time you sign, different signature. It's part of the P6 signing algorithm and whatnot. The way Apple validates signatures has some salt into it. So every time you sign, even though it's the same data, the signature is going to be different. And you can validate you can see here that the data is valid. If I start to modify the signature, you can see the bytes changing in here. It ultimately becomes invalid. So you can validate that this data here is indeed signed by that private key that we're getting. And what's interesting here is you personally don't need a private key or a public key to validate the data comes from someone else. All you need is their public key. So if Walid wants to confirm that the data comes from Dave, Walid only needs Dave's public key, again, which I can put on the website. And so you get the data, you get my public key, and then you get the signature. You can validate the data matches the signature because you have my public key. You don't need anything else. We don't need to exchange keys together in order for the signature to be passed along. I can just generate data. I can generate my data. I can sign it, and I can put it on the system. So if you want to build, let's say you have an app that takes photos. You want to encrypt the photos and put it onto an S3 system. You want to verify that those photos have not been altered by a hacker. What's the way to do it? Directly on your iPhone, you sign the data and you store this encrypted file with the signature on S3. When you go and download the data later on, you can verify that the data is indeed intact and coming from that iPhone because you have the public key of the iPhone and you have the data and the signature. So you're then able to confirm that the files that are on your S3 are indeed coming from your app, from your phone, and they're digitally signed by the right signature that you expect from that user.
Great.
So you're able to confirm that these files will most likely not break your system because they have been created by an authenticated user using the expected version of your app and whatnot. There's still ways to bypass that. But anyway, let's not go into too much detail. But at the very least, you can confirm that the data is indeed intact. And you can also verify if a hacker has uploaded a different file on top of the existing data for whatever reason. They had access to S3 and they were able to get it. Signing does not encrypt your data again.
It's very important.
Signing only validates that the data is intact.
And come from the trust.
And comes from the person that has signed it, or using the private key that has signed it. So if a hacker gets hold of your signing key, your private signing key, they will be able to sign data on your behalf. May not be what you want. So again, use a secure enclave as much as possible to create your private keys.
Great. I think it's great. There is a lot of concept that today we have distinction about signing encryption. A lot of algorithms, ES algorithms, P to 256, and thank you, Dave. A lot of information that people I think have with this episode, and also with I think 5 hours of mobile iOS security along with this 4 episodes. We hope that you find what Dave shared is very important. So I think that we cannot find this information with practical session free in the community. And thank you also very much, Dave, to share all this knowledge. I know that you prepare with your colleague Dia from I think Jordani, a great book about mobile iOS security. I think that we should maybe invite the 2 writers of the book, Dia and you, about a special episode to speak about the book and about iOS security and mobile security. I find what you shared very, very, very interesting to the community. Maybe you have some last thing to say about this 4 episode. What you can find great and something that maybe we can improve in the next episode with you, especially for the next season of the Academy podcast.
Well, for me, I'm very, very happy about being invited and be able to share that knowledge.
Thank you.
Obviously, there's a lot more to security on iOS than there is of just what we shown on those episodes. We're limited in time.
Yes.
Uh, every time I wanted to share as much details as possible about what we're currently covering as topic, but obviously, like file protection mode, we have biometric authentication, we have the keychain, how to store and retrieve information from the keychain. There's a lot of information that is required. So the first thing your viewer should do is go and look at that Apple security platform document that explains all the different security mechanisms that are available on the iPhone and in the Apple structure. It covers secure enclave, the keychain, it's secure the encryption, the protection modes, the biometrics. It covers pretty much everything, and it can explain in details about how they work and how they actually protect you. And then there's a lot of technical sessions that are done at WWDC every year. Unfortunately, a lot of the best session on cryptography and security are years old because that stuff doesn't change nearly as much as Swift UI, for example. We have new Swift
Yes.
UI goodies every single year, but a new crypto
Yes.
goodies every year, not so much.
It's not
So
easy.
you might have to go 3, 4, 5 years ago at the previous WWDC sessions in order to find the sessions on CryptoKit or find the sessions on Keychain. And even the Keychain is starting to be quite dated. When you look at the difficulty on using the Keychain versus using CryptoKit, CryptoKit has a beautiful, simple interface for us to use, but Keychain is still very old and complex to use. This is why you have third-party library like the Swift keychain that you can import into your project that makes using the keychain much simpler. But I wish that Apple had an updated keychain framework that we could use to make that as simple as they made CryptoKit, for example, compared to Common Crypto. Common Crypto was cumbersome, lots of lines of code to be able to do anything, and then CryptoKit made that beautifully simple and almost foolproof, where you cannot use the wrong salt because it's generated automatically for you. I wish they did the same thing for Keychain, honestly, and maybe they will next year. Who knows? But
Yes.
for the users, if they want to learn more, definitely they have to browse a lot more than just this year, WWDC. They have to go 5, 10, sometimes 12 years ago in order to get all of the various sessions. But there's definitely a lot more to cover on the topic. So ask ChatGPT or ask any LLM or ask your Google search engine about what are the topics that I need to learn for mobile security, and they're going to give you lots of different topics, lots of different things. There's some info plist settings that you can enable for improving your security. So just again, do your research. There's some really good. I think it's securing.pl. Let me just confirm. That has a very good, expensive course where they teach mobile security. I think it's $4,000 or $5,000 US. So it's not for everyone, unfortunately.
Yes.
Which is kind of sad that there's not a lot of free training like you're trying to do right now with the community and our tutorials on YouTube, where you provide free training on doing mobile security, because we all gain from knowing more about this, which is one of the reasons I'm doing these sessions with you, just sharing that knowledge. But definitely, if you want to learn more, there's a lot of free resources. You do have to dig for them in the WWDC or in your search engine or some README tutorial like with Medium articles and whatnot. A lot of people have different blogs, but finding and combining all of that information in one big package does not exist for free. And like you mentioned, the book that we're coming with will have a lot of those different pieces in the book, which we're planning on selling at approximately $100, so much cheaper than the commercial courses out there. But still, unfortunately, we have to pay for our labor.
Yes. Thank you, Dave. And I think that you will be with us for this second season. Romance.
I hope so. If you invite me, I'll be.
I invited you. There is no problem for me, and I'm very, very happy to discuss with you other topics about mobile iOS mobile security and other topics, not only mobile security. And as I said, maybe we have you and Dia for the presentation of the book as a special guest to speak about the book, and the main idea about the book. I hope that we will discuss that in the using LinkedIn and other social media to prepare this special episode with you and Dia. I will try to contact
Awesome.
them.
I
For the
just
moment,
remembered,
yes,
by the way, we didn't cover the code of how to generate the signature and validate them. I'm not going to do that right now, but your
okay,
viewer always have access to the project that we can put on the GitHub repository
yes,
for them. So
yes,
please go and look at that project. If you're concerned, if you want to learn how to do that, the code is there and will be available for you.
okay. Thank you, Dave. Thank you. This is the last episode of this mobile security series. There is 4 episodes that you can find as a playlist in the Swift Academy podcast. Hope to see you in the next season that come in February with special guest, which is Tim Condon from from the United Kingdom to speak about BFF, back for front, and Vapor. All this history about BFF backend using Swift and especially Vapor that will be with Tim Condon in February, and so we have other guests that come in this special year. Thank you, Dave, and see you soon. Thank you. Thank you.
See you.